Okay, can you hear me?
Yes.
Yes.
Thank you. Okay, so now let me join this laptop. Okay. Okay, so this part is quite important. It is computing definite integrals over infinite intervals of integration. Okay. Let me record. Plus. Okay, so this is about computing definite integrals over so-called infinite intervals of integration, and it has a lot of applications to economics because basically, usually we want to compute what is called the present value of a flow in continuous time, and at each point in time the element of this flow is multiplied by a discount factor. So very typically we have integrals in which we have to compute integrals by parts. One of the two factors is exponential of minus some function of x, and these integrals are extended to infinite intervals of integration. Okay, so from now to plus infinity, from now to a point in time in the future which is very far in the future. Okay, so you will see an example in a moment. Okay, so basically, in order to compute these integrals, we just have to consider a function which is continuous and a definite integral over some interval between a from a to b. Okay. Okay, so the touchpad is not very okay. From a to b, and what is the meaning of this notation? The integral between a and infinity of f of x dx. it's like having the upper limit of integration, which is plus infinity, instead of just being b, a number, okay? This just has to interpret it in the sense of a limit. It is like the integral between a and b, but b is an upper limit of integration that tends to plus infinity, okay? So, in principle, we should first compute the integral between a and b, and then let b tend to infinity and see what happens. Okay, so this is the basic idea. Provided that the limit exists and is a finite number, of course, in the sense of limits. I mean, the limit must be a finite number in order to be a limit, okay? Not plus infinity. Okay, so, and in a very similar manner, the integral between minus infinity and b is like the integral between a and b, but the lower limit of integration a tends to minus infinity. The second one, this one is not really important in economic applications, but the first one, as b tends to plus infinity, is really important. So just, first of all, become familiar with the notation, okay? And with the meaning of this integral. Of course, writing this makes sense only if the limit exists. I mean, in principle, we cannot write the integral between a and plus infinity of f of x dx if the limit doesn't exist, okay? So we can write this, it is a well-defined quantity only if the limit exists. Okay. The basic example is that of the power function. Suppose that we want to compute the integral between 1 and infinity, where infinity is, if we don't put the sign, is plus infinity, of course, of x to the power of minus a dx. Okay, you can hear me, right? I don't need this one. Can you hear me? Okay. And I hope that, no, because this should work for students at home, right? I guess. Okay. There is an important insight here already, because all the elementary power functions, remember the first class last September, all the elementary power functions of the type f of x is equal to x to the power of minus alpha, where alpha is positive, which means x raised to a negative exponent, okay, real exponent, have all qualitatively similar graphs over the interval between 0 and plus infinity, okay? All qualitatively similar graphs, because the graph is like this. It's kind of similar to a branch of hyperbola, okay? As x tends to 0, the graph tends to the vertical asymptote to plus infinity, basically. As x tends to infinity, the graph tends to 0. All have the same graph, qualitatively. The only difference is, let's say, the speed with which this branch of the graph approaches 0. Some of them are slower and some are faster. The larger is the exponent alpha, the faster is the convergence to 0 of this branch, okay? It approaches 0 it is faster in approaching 0. Suppose that you want to compute the integral between 1 and infinity of x to the power of minus alpha dx. In principle, we want to compute this area between the curve, the horizontal axis, starting from 1 and up to plus infinity, okay? It's quite intuitive that if this branch approaches 0 very quickly, it should be possible to compute that area. But if the convergence to 0 is slower, it's likely to be impossible to compute that area, okay? I mean, when you increase x, you add a small piece of this area, okay? You add a small piece to this area. If these pieces that you add by increasing x become smaller and smaller sufficiently fast, then your area converges to a finite number. But if they become smaller and smaller, of course, but not fast enough, the process doesn't converge, so you cannot compute the area, a well-defined area. So basically, in the limit, you see that it is plus infinity. It's not a number. So what is the threshold between being able and not being able to compute the area? The threshold is alpha equal to 1. If alpha is larger than 1 here, for instance, x to the power of -2, then you can compute that area. But if alpha is 1 or smaller than 1, yet negative, but smaller than 1, minus alpha is negative, but alpha is smaller than 1 or 1, you cannot compute the area. So the threshold is 1, okay? And we can see it very easily if we apply the definition of this, this limit, okay? Because first we compute the integral between a and b of that quantity, and then we take the limit as b tends to infinity. And we see it very clearly that the threshold is 1. Why is that? Because if we compute this integral, this is an elementary integral, it's minus alpha plus 1 at the new exponent here, divided by minus alpha plus 1, and this is a primitive of this function, and we have to compute this primitive in b and then subtract the value in 1, okay? The primitive computed in b is it's b to the power of 1 minus alpha, and computed in 1 is just 1, okay? So we get this primitive. Then we can just change the sign here and here just to have a more friendly notation here. 1 over alpha minus 1 times 1 minus b to the power of 1 minus alpha. Now, suppose that alpha is larger than 1, for instance. So instead of having a negative exponent here, you can put this in the denominator, okay? Though this is more intuitive, because now suppose that alpha is larger than 1 for a moment. You have b, which is typically, remember that here you have to compute from 1 to b, and then to let b go to plus infinity. B is larger than 1, so b is positive, okay? B is a positive number. To the power of alpha minus 1, which is a positive exponent, what happens to the denominator here? As b tends to infinity, it goes to plus infinity, okay? So this part here disappears, and you are left with 1 over alpha minus 1 as the limit. This is a positive finite number, because alpha is larger than 1. If alpha is equal to 1, you cannot use this formula to compute the integral, because it's the case of the log. We see it in a moment. But if alpha is less than 1, what happens here? Now it is 1 minus alpha, which is positive. So here you have something that goes to infinity. Okay? So you don't have a finite limit for this area as b tends to infinity. So this, applied the definition, shows that the only cases in which you have an area that converges to a finite number is when alpha is larger than 1. Here you see that when alpha is smaller than 1, for instance, 1/2, okay? We would have here 1 over the square root of x. Qualitative graph is similar to this one, but the area doesn't converge. And the only case which is left for our analysis is when alpha is exactly equal to 1, so the function is this one, x to the power of minus 1. Its primitive is the log of x. Between 1 and b means the log of b minus the log of 1, which is the log of b. because the log of 1 is 0. Take the limit as b tends to infinity of the log of b is plus infinity. So it doesn't work with alpha equal to 1, it doesn't work with alpha between 0 and 1, it works only when alpha is larger than 1. Okay, so this is the basic insight from power functions. So not all power functions of this type with alpha positive and a negative exponent, then not all functions of this type have a finite area, let's say, when I compute the integral between 1 and infinity. Only those with alpha larger than 1. Okay. For instance, in this case, we have an example with alpha equal to 3 over 2, which means computing the integral between 1 and plus infinity of 1 over the square root of x to the power of 3 dx. Okay? I can use the formula already ready to use because we derived it in the general case, because the general case not only tells us that the limit exists, but also tells us that the value of the limit is this one, 1 over alpha minus 1. So the integral between 1 and infinity of x to the power minus 3 over 2 dx is 1 over 3 over 2 minus 1, which is equal to 2. Okay? So for instance, suppose that you don't remember the formula. You have to compute the integral like this. For instance, okay? We know already that there is a convergence to some finite value here because alpha is larger than 1. Okay, but let's compute our integral. We have to find a primitive. I apply the step-by-step method first. We have to compute a primitive which is minus 1 over x. Okay? It's minus 1 over x. This must be evaluated between 1 and b, and then I have to take the limit of this as b tends to infinity. Okay? So it is minus 1 over b plus 1. So it would be minus 1, okay? Plus 1. Okay? And the limit here is, as b tends to infinity, you have here minus 1 over something that tends to infinity, it becomes 0, okay? This is equal to 1. In practice, we don't do that. We don't do this step. We don't write the limit when we show the computations of this. We just write something like this. Once we have found a primitive, we evaluate the primitive directly between 1 and infinity, which means that, of course, I cannot replace infinity here. This means implicitly that I have to compute the limit as x tends to infinity, okay? But the limit as x tends to infinity is just 0 minus 1, which is 1, okay? Clear? Now, suppose that you want to, of course, the property of additivity with respect to the interval of integration holds also in this case. So, for instance, if you have this function, Suppose that this function is our y equal to 1 over x squared. I want to compute the integral between 1/2 and plus infinity. And then I want to compute the integral between 1 and plus infinity, which is the double shaded area, okay? Clearly, this is just an example, but clearly the integral between 1/2 and 1, the integral between 1/2 and 1 of 1 over of x to the power of minus 2 dx can be regarded as the integral between 1/2 and plus infinity minus the integral between 1 and plus infinity, okay? Because this has the meaning of an area, even if it lies below a branch that goes, I mean, it is not a finite area, okay? But you can regard this area here as the difference between the area from 1/2 to plus infinity and the area from 1 to plus infinity, okay? So you can write that it is the difference between the integral between 1/2 and infinity of x to the power minus 2 dx and the integral between 1 and infinity of x to the power minus 2 dx. What I mean, and this property of additivity of areas, which means it is called technically additive property with respect to the interval of integration, also in the case of infinite intervals, okay? You can, I mean, if you don't believe it, just compute this integral, make the difference, and you will get the integral between 1/2 and 1 of the same function, okay? So it's a useful, it is also a useful exercise. So when we don't have convergence, we cannot write something like this, because it is not a well-defined quantity. Okay, so now we have an example with a very simple example that has also an economic interpretation. Suppose that you want to compute the integral between 0 and capital T. Now my variable T is, ideally it is time, okay? So from time 0 to some time horizon, capital T, of exponential of minus 0.05 t dt. So what is the meaning of this? You can regard this as 1 times exponential of minus 5% t, okay? In this case, we have a flow, for instance, a flow of money, of income, with a very simple structure. It is constant at the level 1, which means 1 unit per year, okay? 1 unit, monetary unit, per unit time. It depends on what is the unit time in which you measure t, okay? Usually year. So it is 1 here means 1 euro per year. If I have 100 here, it's 100 euros per year. But it is uniformly distributed over the year, technically speaking. So if I have 1 euro per year, I have 0.5 euros every 6 months, 0.25 euros every 3 months, and so on and so forth. So this 1 euro per year is uniformly distributed over the year. So it is a flow, okay? It's like having a small piece, or a small part of this euro for every sub-period, ideally, with sub-periods that have a length that goes to 0, very short, daily, for instance. So it's like having 1 euro divided by 360 per day, okay? It's like this. So it is a flow. And each of these is then discounted with this. This is called discount factor. A typical expression for this discount factor is the exponential of minus some interest rate, this is 0.05 for instance, times t. What is the meaning of multiplying this 1 by this factor? The meaning is that if this €1 is immediately, okay, it has to be multiplied by 1. So its present value is the same as its nominal value, okay? But if I have €1 which becomes available in 1 year, so its present value is smaller, okay? It is multiplied by a factor that reduces its value, and the value is reduced, the reduction is larger and larger for larger t. So the same euro in 2 years is worth less than the same euro in 1 year, okay? This is the basic idea. This is called discount factor. So basically, apart from this interpretation, this is the integral between 0 and capital T of a constant flow, unit flow in this case, times a discount factor, which is a function of time, of course, dt. A primitive of this one, since this is 1/20, a primitive is minus 20 times exponential of minus 1/20t, which must be evaluated between 0 and t, and becomes minus 20 times, replace capital T here, and then subtract 0, replaced here. Exponential of 0 is 1, so you get this, but of course remember that this is smaller than 1, so we can just put 20 here and put a positive quantity into the brackets. So this is the result, okay? So the present value of a constant flow of €1 over a time horizon of 10 or t equal to 10, for instance, years, is 20 times 1 minus exponential of 0.05 times, for instance, 10 years, okay? Times 10. What is the integral between 0 and infinity of this quantity? If you have the integral between 0 and infinity, you just have to let t, capital T, go to infinity in this one, in this expression, okay? If t to infinity, this goes to 0 and the result is 20. So what is the interpretation? So for instance, in the first example here, if t is for instance 20 years, you have a constant flow of €1 per year, equally distributed over the year, but €1 per year, okay? Over 20 years, what is the present value of the 5% rate? It is only 12.64 euros, so it is not 20 euros. 20 euros is a nominal value of all the 20 euros over the 20 years, but it is depending on the date where these euros become available, they are discounted, okay? So the total aggregated value of the discounted sum is this one. And if the flow lasts forever, which is the meaning of taking this limit, one would say, okay, it's infinitely many euros. No, infinitely many euros is the nominal value. The present value is just 20 euros, okay? So what really matters is basically the last few decades, okay, in this kind of computation. And of course, the result depends on the rate, on the interest rate. Because if the larger is the interest rate, the smaller is the result. And the smaller is the interest rate, the larger is the result, okay? The interest